Welcome to problem solving session by the course Introduction to Information Theory on NPTEL. I'm your TA Sachin from the EC department in the Indian Institute of Science. Today, this week's topics were rate distortion theory and Blahout Harimoto algorithm, but I don't think there are any questions based on the algorithm. So all the questions are from the lecture on rate distortion theory. Start with question one. Consider a Bernoulli source with equals half and the Hamming distortion measure with capital D equals 0.2. What is the rate distortion function for this source? I'll give you 2 minutes to try it yourself. Then I'll come back and give you the answer. Right, I'm back. So we saw in the lecture for a Bernoulli source rate distortion function. Rate distortion function for a Bernoulli source with parameter P with Hamming distortion is given by R of D equals H of P minus H of D if D is between 0 and minimum of P comma 1 minus P. It is 0 if D is greater than minimum of P comma 1 minus P. If you're given choices like multiple choice question, you can see that in the given choices, that's not 0, so you don't have to worry about that option. But it is not multiple choice, then you would have to find P is half, which means 1 minus P is half, and their minimum is also half. D is 0.2, which is less than half. So R of D is H of P minus H of D, which is equal to HR is zero point 0.5 minus HR 0.2. It turns out to be 0.278. I'll leave the computation to you. H of zero point 0.5 is 1. H of zero point 0.2 will have to go to a table and see what H of zero point 0.2 is and then subtract that from 1. Question 2, considering the same source as given in Q1, what will be the rate distortion function for t is equal to 0.7? Chances are 0, 0.47, 0.53, and 1. So the source is Bernoulli source of parameter P and Hamming distortion capital D. For such a source, we saw in question 1, depending on the value of capital D and small p, R of D is given by this function. So if D is between 0 and minimum of p comma 1 minus p, R of D is h of p minus h of t, where h is the binary interval function. If capital D is greater than minimum of p and 1 minus p, then R of capital D is 0. You don't need any bits to represent the value just decode. You reconstruct to a single value all the time, and your distortion value. So if D is greater than minimum of p comma 1 minus p, then you can always just reconstruct to a single value. So you can reconstruct to either just 0 or 1 all the time, and the distortion condition will be met. And distortion will just be D in that case. I'm not sure if that was explained directly in class, but distortion is the average value of overall x in script x. So for Bernoulli random variable script x is 0, 1. And x hat in script x hat, I guess. Script x hat and choose it to be 0. Or let's keep it at that one. Then this will be p of 0 dr 0 comma x hat plus p of 1 dr 0 comma x hat. P of 0 is 1 minus p dr 0 comma x hat plus p of 1 is just, sorry, that's not right. That's not the distortion. Give me a minute. Um, yeah, D was summation P of x, D of x comma x hat for all x. And since we are using the Hamming distortion, then if x hat is not equal to x, D is 0. Let me also write that down. For Hamming distortion, D of x comma x hat is 0 if x is equal to x hat, 1 if x not equal to x hat. So let me get back to that later. Okay, I forgot what point I was trying to make. Uh, Anyway, the rate distortion function is h of p minus h of p. If d greater than or equal to 0 less than the minimum of p comma 1 minus p. It is 0 if d greater than minimum of p comma 1 minus p. And since we have the same source as the previous question, p is half, which means 1 minus p is half, which means the minimum of p comma 1 minus p is half. The difference in this question is d is 0.7, which is greater than half. Since it's greater than half, R of d is 0, which is option E. Here the option was 0.278, option B. Okay. Point I wanted to make was that so for Hamming distortion function, we have distortion d of x comma x hat is 0 if x equals x hat and 1 if x not equal to x hat. So the distortion is the expected value of the distortion e of x comma x hat is e of d of x comma x hat is what is it? It's 0 probability x equals x hat plus 1 with probability x not equal to x hat, which is nothing but p of x not equal to x hat. And for the Bernoulli source, p of x not equal to x hat is p. Sorry, not p. Um, what am I saying? Wait. Okay. Um, d is summation p of x, um, d of x comma x hat for all x in script x. For Bernoulli source, script x is 0, comma 1, and p of 0 is 1 minus p, p of 1 is p. So it's a Bernoulli source. It's not the. I was getting confused with the binary symmetric channel. That's why I was in a train of thought. But it's the Bernoulli source with the probability of emitting a 1 equal to p and probability of emitting a 0, 1 minus p. Suppose I have Suppose I set x hat equals 0 always. So all probability 1. So regardless of what the code word index is, I always reconstruct to 0. Then this summation d is probability of 0 d of 0 comma 0 with probability of 1 d of 1 comma 0 because x hat is always 0. D of 0 comma 0 according to this Hamming distortion is 0. So this is p of 0 into 0 plus p of 1 into d of 1 comma 0 is 1 is not equal to 0. So it's for x not equal to x hat, it is 1. So there is 1. So p of 1, which is just p. So for this uh, code, where the reconstruction is just x hat is equal to 0 always. Uh, the rate is 0 because I don't need to use any code word. I don't need to do any coding, right? Every input for whatever input there is, I'll always give you the reconstructed output x hat to be 0, for which I don't need to do any coding. So my rate is 0, and also I have achieved a distortion of P, which is our aim when we are trying to find a rate distortion function. So we need an achievable rate, and we have to, um, if for a fixed distortion, we have to minimize the rate. The minimum rate you can get is 0, and your distortion must also be within a certain, the distortion will be given. That's why this for D greater than minimum of P comma 1 minus P. Uh, you can always achieve the distortion equal to P and use a code operate 0. Anyway, even if you didn't understand that part, as long as you know what R of D is for a Bernoulli source, you can solve this question. Maybe it was explained in the lecture also. You can go back and watch the lecture video. Question 3 is, what is the optimum 1 bit quantization of a single standard Gaussian random variable under squared error distortion? The options are plus or minus 1, plus or minus 2 or pi, plus or minus 1 or pi, plus or minus square root of 2 over pi. So when you're doing 1 bit quantization, you have 1 bit quantization. So you have 2 power on two values in script x hat. Right, your reconstruction can have two values. So you have x, which is real valued since it's a Gaussian random variable, and then you for each value uh, uh, there's a density function for this Gaussian random variable of x, something like this. Now you have two code words only, and you have to assign, you have to split this into two regions, such that when the code words, when the x value is written in one region, you assign, you encode it to that particular code word, and when your x value is in the other region, you encode it to the second code word. So you have to split it into two regions, and then you, you have to reconstruct. When you receive a particular code word, you have to reconstruct it to a particular value of x. So that is to say, since it's one bit, suppose for all values of x greater than or equal to 0, I assign a code word 1 for all negative values. I assign the code word 0. So this is 1 bit. Now, if my x value, my random variable x takes some value, say 5, then I encode it to 1. Let's say I send it, transmit it, or store this one somewhere. Then someone else comes and looks at the one, and now from this one he has to reconstruct the value of this uh, random variable x. So from this one he has to give you an estimate of x. So this estimate of x is again a real number, but see, all values x that are greater than or equal to 0 have been encoded to the same code word 1. So while you are reconstructing, since it's like a function, there's only one value to which you can reconstruct this, and you don't know which uh, input was actually encoded to 1. You don't really know that. You only know that the value which was encoded, this x value, was a positive number. So now you can reconstruct the code word 1 to some positive number a. Similarly, the optimum way to do it is to reconstruct negative numbers to negative of a. Which value a you should choose? You should choose a value a such that the expected value of the square error x minus a whole square is minimum. What is the expected value of x minus a whole square for a Gaussian random variable with mean 0 and variance 1? It's, you know that uh, if you have received If you're reconstructing to A, then the number is a positive number. So the expected value of x minus a whole square is x minus a whole square divided by square root of 2 pi e power minus x square by 2 dx. And the optimum value derivative of, let's call this f of a with respect to a is 0. You should have seen in calculus when you want to find the minimum and max value, you take the derivative and set it to 0. So the derivative is with respect to a because that is the parameter which we are changing to maximize or minimize this function. So derivative with respect to a is 2 into x minus a divided by square root of 2 pi e power minus x square over 2 dx. You set this to 0. You can take the square root of 2 pi uh, away since this is 0. Then you can write, you can split this integral into two parts, 2x power minus x square over 2 dx. Root 2 pi is equal to a, I'll keep it because I'll keep the root 2 pi because I need it in the next step. So this is equal to integral 0 to infinity 2a by square root of 2 pi e power minus x square over 2 dx, which is 2a times integral 0 to infinity. I don't need the 2's, I guess. So I can take away the 2 here. Maybe I mean the constants can be taken out of the integration and then we can divide both sides by 2. So it you can take out the constants. I will keep the 2 pi because it's useful. Now this is integral 1 over square root of 2 pi e power minus x square by 2 dx. And this thing is 1, right? Because it's the thing inside is the density function of a Gaussian variable. Actually, oh, it's integral only from 0 to infinity, so it's actually half because Gaussian distribution is symmetric, and the integral from minus infinity to infinity is 1. So integral from 0 to infinity is half. So that case I should just keep the 2 which is equal to 2a into half, they'll get a. So a is integral 0 to infinity root of 2 over pi into e to the to 2 over pi x into e power minus x square over 2 dx. Now can do substitution. Y is minus x square over 2. Then x equals 0, y when x equals 0, y equals 0, when x equals infinity, y is minus infinity, and dy is minus dx. So a is integral 0 to minus infinity minus square root of 2 over pi. So the dy is derivative of, can take out the half outside, derivative of x square is 2x, but it's the differential is 2x dx. So it's minus x dx. So x dx is equal to minus dy. So this becomes e power y dy. Or you can integrate from minus infinity to 0, root of 2 over pi, e power y dy. Integral of e power y is just e power y from minus infinity to 0, which is root of 2 over pi, e power 0 is 1, minus e power minus infinity is 0. So a is square root of 2 over pi. This is the case for normal distribution with mean 0 and uh, variance 1. For distribution 0 comma sigma square, a is square root of 2 over pi, and we'll have, let me see, square root of 2 over pi sigma. So x hat of x is square root of 2 over pi sigma if x greater than equal to 0, minus root of 2 over pi sigma if x less than 0. In our case, sigma is 1, so we get root of 2 over pi if x greater than equal to 0, minus root of 2 over pi if x less than 0. You can also check and see what happens if the mean is not 0, if it's a shifted version of the Gaussian curve. So the answer is plus or minus root of 2 over pi, which is D. I I don't think that was done in class. Was it done in class? I did the derivation anyway. So for single bit quantization, this is straightforward, right? The optimum will be to divide it into two regions, one from one region with positive values and another region with negative values. And when you are reconstructing, you reconstruct to the mean value, the value which minimizes the mean square error. Suppose you had to do two-bit quantization, then you would have to divide this into four regions. But what regions you should divide this into, it's not a straightforward question. So there's no straightforward answer for this. You can do it easily only when there are two regions. And then once you divide it into regions, which value you have to choose within the region, that's also not easy to calculate most of the time. Maybe you could do it for the Gaussian distribution, but if there are other distributions. So these are the main problems when you are trying to quantize a source with finite number of bits. So which region you have to choose so that by choosing the region, you're choosing uh, all the values which go to the same code word. So the problem here is that if you want to represent a real value with the bits, then unless you have an even if, unless you have an infinite number of bits, you can't exactly represent each real value. So if you have only a finite number of bits, there are only a finite number of code words you can form. So uh, some of the values will have to be encoded to the same code word. So you divide into regions like this, and all the x values in this region will be encoded to the same code. Now, when you do that, you are actually losing information. So, when you are reconstructing, that is going back from this code word to some value here, you don't you don't know exactly which value is actually encoded. So you have to choose some value arbitrarily according to some rule. The rule you use is you choose that value which minimizes the distortion. But which value minimizes the distortion, that will depend on the distortion measure, on the region. The, so it's not straightforward. Anyway, next we will move to question 4. For Q3, what is the corresponding expected distortion for 1 bit quantization and the achievable distortion rate bound for R equals 1? Is it 1 over 4 comma half? half comma half, 5 minus 2 comma 5, minus 2 over pi comma 1 over 4, or 5 minus 2 over pi comma half. So the expected distortion is minus infinity to 0 x plus a whole square by square root of 2 pi e power minus x square over 2 dx plus integral 0 to infinity x minus a whole square by square root of 2 pi e power minus x square by 2 dx. The expected value of x is integral of x f of x dx from minus infinity to infinity. Here the expected value is of the uh, square of the error. So if x is the value that was sent, you reconstruct to value a, then error is x minus a, and square of error is x minus a whole square. And this error, the density function is the Gaussian distribution because you are transmitting the Gaussian distributed random variable. So for x greater than 0, less than infinity, you reconstruct to a, so it's the average error is squared error is integral 0 to infinity x minus a whole square by square root of 2 pi e power minus b squared by 2 dx. And for negative values of x, you reconstruct to minus a. So the average square error is x plus a whole square f of x dx. And you can further simplify this. X plus a whole square and x minus a whole square both have terms x square plus a square common. So you can write it as x square plus a square by square root 2 pi e power minus x square over 2 dx plus uh, from minus infinity to 0 you have one more term which is 2ax by 2ax into f of x dx. And for x minus a whole square term you have minus 2ax, but uh, for the term containing 2ax, you are integrating from minus infinity to 0, and for the term containing minus 2ax, you are integrating from 0 to infinity. Again, you can simplify the integral yourself. You will do a substitution, and you'll get that both the terms are the same. So you will get minus 2 times integral of 2ax by square root of 2 pi e power minus x square over 2 dx from 0 to infinity. Now I leave the integration part to you. It's too lengthy, but it's not too complicated. this will turn out to be 1 plus a square minus 4 over root 2 pi root of 2 over pi, which will be 1 plus for a is equal to root of 2 over pi, 1 plus 2 over pi minus 4 over pi, which is pi minus 2 over pi. So for 1 bit quantization, that's the expected distortion. So that's by using the uh, reconstruction that we had for the that we that I explained in the previous question. The rate bound was done in class. The achievable distortion rate bound uh, was D is sigma square 2 power minus 2r. This was explained in class. This is for a Gaussian source distributed according to distributed according to the Gaussian distribution. It means 0 and variance sigma square. So there was a bound. You have to minimize I of x comma x hat, which is h of x minus h of x given x hat, and h of x is half log of 2 pi e sigma square. H of x comma x given x hat can be written as h of x minus x hat given x hat. And when you're bounding it, you can drop the conditioning, so it will become half log 2 pi e sigma square minus h of x minus x hat. And h of x minus x hat is a differential entropy, and differential entropy itself is bounded by a normal distribution. So you end up with a half log of sigma square over d. R of d is equal to half log of sigma square over d. If you rearrange the terms, you'll get d is equal to sigma square 2 power minus 2r. This you can go back and see in the lecture. Now they have given sigma square is 1 and rate is 1, so d is 1 into 2 power minus 2, which is 1 over 4. So that's the achievable disruption. Okay, question 5. Consider a memoryless Gaussian source with mean 0, variance 1, with mean squared error distortion with b equals half. What is the rate distortion function for this source? Options are -1, 0, 0.5, and 1. The derivation for rate distortion for a Gaussian random source was explained in class, so I won't go into the derivation. The rate distortion function for a Gaussian distribution between 0 variance sigma square with squared error distortion is given by R of d is half log of sigma square by d. If d is between 0 and sigma square, it's 0 if d is greater than sigma square. So here we have what is d? D is half, sigma square is 1, so d is less than sigma square, greater than 0. That condition is satisfied. So R of d is half log of, you want it in bits, is base to 1 over 2, which is half log of 2 to the base 2, which is just half into 1. So with this mean square distortion half, you can, the minimum rate you can go to is half. bits per use, I guess. Which is option C. Question 6. Consider a memoryless Gaussian 01 source with mean squared error, distortion d equals 4. What is the rate distortion function for this source? So the setting is similar to the previous case. The rate distortion function is the same. The difference here is that distortion value d is 4, which is greater than sigma square, which is 1. So R of d is 0. So R of d is 0 just means that the rate is 0, which means that you don't need to do any coding at all. So if you're given a real number, then you're you don't need you don't need to quantize it or do anything. You can just say I will return a value, any arbitrary value you want, since it's a continuous random variable, and the distortion that you get will still be less than d. So in a sense, the distortion that they're expecting of you is too large. So you don't even need to do any coding to get that amount of distortion. If you increase the rate, the distortion will become lesser and lesser, and if you uh, reduce the rate, the distortion will become more and more. So for a particular value of distortion, how much can you reduce the rate is what is known as the rate distortion function. But if what they expect of you, the distortion that they allow you to have is very large, then you don't need to, you can reduce the rate as much as you want. That is, you don't need to do any proper coding. And just by the nature of your source, your distortion will be less than the required quantity. If I could explain that with the diagram, suppose this is the distortion and this is your rate. What you're doing here is you have a random variable x which just has too many values in it, and you have a code, let's say C, with less number of values than the number of values in x. Suppose this is the set of real numbers, and this is just uh, let's say there are n bits, so you have 2 power n values in your code. Then all the set of real numbers have to be encoded into just 2 power n values. So what happens is you are compressing, you are getting compression, right? So this has infinite amount of bits of information. You need infinite bits to represent this real value source, but you are representing with a finite number of bits, so you're actually getting some sort of compression. Even if this is not R, let's say this is 2 power n, where n is greater than, much greater than n. So a large number of values are getting to a smaller number of values, so you're getting compression. But you're also losing information in the sense that this mapping can't be one to one because there are more values here and less values here. So it's not a bijective function, this encoding. It's the encoding is not one to one when you're trying to decode the decoding also, but decoding has to be one to one because the decoder doesn't know the details. So since it's a many to one function, when you're going back, there's no in the sense of functions, there's no inverse function here. There's just an inverse set. There's a set of values from which you could reach a particular value of this range. But if you have to select only one of these guys, then suppose you send this value, but you go back to this value, then there's some difference between these two values. So that's the distortion. By using larger and larger codes, so instead of 2 power n, if you use 2 power n dash, where n dash was much larger than n, but it is still less than capital N, you're using a larger code, so the distortion you get will be lesser. Because so what you can do is most of the time this rate versus distortion curve will be like this. If you increase the rate, you can reduce your distortion as much as you want. But if you decrease the rate, as you decrease the rate to lesser and lesser values, your distortion. Is this the right curve? I can show you an example. Instead of drawing an arbitrary curve. So for a Bernoulli source, which we did in the first and second question, we had a Bernoulli source. We calculated R of D for that. If you draw the curve h of p minus h of d, it will be so r of d is h of p minus h of d if d is between 0 and minimum of p comma 1 minus p. So minimum of p comma 1 minus p will be less than or equal to half all the time, right? Because p is between 0 and 1. If p is greater than half, then 1 minus p will be less than half. If p is less than half itself, then that is the minimum value. So the minimum must be less than zero point 0.5. So d less than min of p comma 1 minus p can only happen if d is also less than zero point 0.5. So the r versus d curve will stop at zero point 0.5. And here you can go up to rate 1. In which case, when you are doing rate 1, that means the number of values in x and number of values that script x hat can take, both are the same. So that's a one-to-one mapping. So you're not really getting any compression. So when there's no compression, it's error free. There's no distortion. But if you so now let's say I tell you that D should be here, right? You can use any rate between 0 and 1. So the minimum rate you can use is 0. But suppose I tell you that D is somewhere here, I give you a value here, let's say 0.25. Then if you decrease the rate below this value, your distortion will increase. It will go beyond 0.25. So the minimum rate you can operate at will be somewhere here. Maximum rate will still be 1. If I ask for even smaller distortion value, the minimum rate will be higher. So you need larger rates to get smaller distortions. Now, in the previous question, what happened was d was less than sigma square. So this is not the Bernoulli source. This is the Gaussian source. But even for the Gaussian source, the function is something like this, except that instead of zero point 0.5, this is sigma square. So for d greater than sigma square, minimum is 0. So it will be something like this. So in this question number 5, d was less than sigma square. So it was somewhere here. So the minimum rate you could use was greater than 0. The minimum rate in this case is R. But in this question number 6, the distortion that they are allowing is somewhere here. It's 4, much less than in sigma square. And actually, it is somewhere here. So to get distortion less than this, you can use any rate you want. So the minimum rate you can use is 0. That's just because uh, its rate is k over n, the number of, or it's a log of the number of messages, that number of code words that you have. If you have 2 power r code words, then you can represent it with r bits, where r is the rate. So lowest it can go is 0. If this r becomes negative, log of 2 power some negative quantity, 2 power negative quantity is less than 1, log of some quantity less than 1, which will be negative. So I would be saying that I need a negative number of bits to represent a code word. Doesn't make any sense. So lowest you can go is 0. But from this curve, you can see that if the distortion is larger than sigma square, then you can achieve it even with rate zero. So you don't actually need to do any coding. So that's kind of a qualitative explanation of the rate distortion function and the distortion. I don't think that was done in class, but you can refer to Thomas and Cover, Elements of Information Theory by Thomas and Cover, which is one of the reference textbooks. There you can see some of the graphs of R of D versus T and some of the derivations and proofs from the lecture are also taken from this textbook. Examples of. Okay, we go to question 7. Consider a source X uniformly distributed on the set 1, 2, 3 up to 8. Find the approximate rate distortion function for this source with Hamming distortion at D is equal to 0.25. Options are 2.81, 1.89, 1.49, none. I won't be going to the details of the derivation because it was done in the lecture and you can go and watch the lecture video. But in this case, the rate distortion function with Hamming distortion for a source X, which is uniformly distributed on the set. I'll give you the general result, which was derived in class, set 1 to 3 up to m values. In that case, the rate distortion is given by log of m to base 2 minus h of d minus d of d times log of m minus 1 to base 2 if your d is between 0 and 1 minus 1 over m. It is 0 if your d is greater than 1 minus 1 over m. In this case, m is equal to 8. X takes the values from the set 1 to 3 up to 8. 1 minus 1 over m is 1 minus 1 over 8 is 7 over 8, which is what? 7 into 125 by 1000, 0.875. So D is 0.25, which is less than 0.875. So the rate is the first function value. R of D is log of M log of 8 to base 2 minus h of D h of 0.25 minus 0.25 times log of 7 to base 2. So I'll leave the computation to you. Here h of D is the binary entropy function with evaluated at D. So you can look it up from a table online. So maybe there's a calculator for binary entropy function. You can find that. Or you could calculate binary entropy. H of P is nothing but minus P log P minus 1 minus P log 1 minus P. So if it's in an exam, you have to plug in the value of P in that function. And this will turn out to be 1.487. It's close to 1.49. Say 1.49. Question 8. Considering the same source as given in Q7, what will be the rate distortion for p equals 1? B is greater than 1 minus 0.875, so the rate distortion is just 0. Option. Question 9. Let xi be distributed according to n of 0, comma sigma I square. I is equal to 1 to 3. So 3 random variables, random sources, Gaussian distributed with mean 0, and there are they're independent Gaussian random variables, and sigma 1 square is 1, sigma 2 square is 2, sigma 3 square is 4. Let distortion measure be d of x cube comma x hat cube is, it's not 3x cube, it's vector x power x to the n. three-dimensional vector, which is I is equal to 1 to 3 xi minus xi hat whole square. So it's again the squared error, but sum of the squared errors. So what is the rate distortion function for d equals 3? The options are 1, 1.5, change the color, I think. Let 6 or none of the above. So this is a parallel Gaussian source. So the rate distortion function for a parallel Gaussian source is R of D equals, so it's just the sum of uh, rate distortion functions. So for a single Gaussian random source, we saw that R of D was half log of sigma square by D if D is between 0 and sigma square. We have multiple channels. It's the sum of half log of sigma I square by di. But the thing is, the di, there's no di in the question, right? The total distortion that is allowed is b, which is 3. So we had a similar type of thing. What was it? Power allocation for doing channel capacity of parallel Gaussian source, parallel Gaussian random elements, and we did the optimum was to do water filling of the power. So the optimal power allocation for parallel Gaussian sources. This is not water filling, but it's kind of similar. It's a reverse water filling or something. It's kind of opposite of water filling. So di is lambda if lambda is less than sigma I square, sigma I square if lambda is greater than or equal to sigma I square, where lambda is chosen so that summation of di is equal to 1 to m is equal to d. So here sigma 1 square is 1, sigma 2 square is 2, sigma 3 square is 4. Uh, Sigma di I is equal to m I is equal to 1 to 3 is in our question 3 since d is equal to 3. So you have three channels. This is at level 1, this is 2, this is 4. Right? You have to select a lambda level somewhere here. And then if your sigma square is less than lambda, you take this as the oh, I made a mistake while writing this. Lambda is lambda is lambda is less than sigma square. Sigma square is lambda is greater than or equal to sigma square. So if this so if it is like this, if you choose your lambda like this, then lambda is greater than sigma square for this value and this value. Then you will have to add these two sigma squares. And sigma square is greater than sigma 3 square is greater than lambda. So we'll have to add lambda to it. And this sum should be equal to d. So what that means is 1 plus 2 plus lambda equals 3. Or lambda equals 0, which is not true. If lambda was 0, it wouldn't be above 1 and 2. So I picked lambda above 1 and 2. So I can't do that. I have to bring my lambda level lower. I have to bring it so low such that it's below the next highest sigma I square. If I do this, if I choose that as my lambda, then what I get is um, sigma 1 square is lambda is greater than sigma 1 square, so sigma 1 square. Lambda is less than the second one, sigma 2 square. So this is lambda and this is also lambda. This is equal to d, in which case sigma 1 square is 1. 1 plus 2 lambda is equal to 3. So 2 lambda is equal to 2. Lambda is equal to 1. So this is possible because this 1 lies between the two levels 1 and 2. So you could take your lambda here and you would get sigma 1 square plus lambda for that also. So lambda equals 1. Right? And so that's the method. You start out at a lambda value greater than all the values of sigma 1 square. Then summation of di will just be summation of sigma I square. Check if that value is equal to d. If that value is not possible, then bring it below the highest sigma I square value. Then check if it satisfies the condition sigma di is equal to t. If that's not possible, bring it again below uh, the second highest value. Keep doing it, and for some particular value of lambda, you'll end up uh, with values of lambda and sigma squares, which add up to d. Suppose if sigma a square, there's some is already uh, greater than the given distortion d, then your R of t will be 0, similar to the previous questions. If your d is greater than sigma square, you have R of t is 0. Sorry. Uh, that can't really happen because you are going from the you can lower your lambda value to below the smallest value such that it will still satisfy the distortion constraints. Because if lambda is less than sigma I square, then uh, di is lambda instead of sigma I square. So I'm not sure if there is a configuration of sigma I squares and distortion constraint d for which this won't work, but the method is still the same. You start out at the top and keep going lower and lower until the constraint is satisfied. So here we saw for this particular question, lambda is 1. So di is lambda if lambda less than sigma, sigma I square. It is equal to sigma I square if lambda greater than equal to sigma I square. So 1 is greater than equal to sigma 1 square. So it is equal to d1 is equal to sigma 1 square is 1. D2 is also 1. D3 is also 1. So D is summation of D1 plus D2 plus D3 is 3, which is what was required. Now you just have to find R of D is half log of sigma 1 square by D1 square, which is 1 over 1, plus half log of sigma 2 square by D2 is 2 over 1, plus half log of sigma 3 square by D3. Sigma 3 square is 4, which is half log 1 is 0, half log 2 is 1, half log 4 is 2, so this is just 0.5 plus 1, so 1.5. That's how we do it for a parallel Gaussian source. Alright, we'll finish the session with the 10th question. So, following the problem of Q9, what will be the rate distortion function for d equals 4? Is it 0.5? Is it 1? Is it 1.25? Is it 0.915? Yeah, 4 to 1. And so if we start out here, then you would get um, lambda plus lambda plus lambda, which is 4 plus 4 plus 4, 12, which is obviously greater. If you go somewhere here, then summation of di is 1 plus 2 plus lambda, which is equal to 4 means lambda equals 1. But from the diagram, I have chosen lambda greater than 2, so lambda equals 1 is not possible. So lambda must have been lower. I choose it somewhere here, then I get 1 plus 2 lambda is equal to 4, or 2 lambda is 3, lambda is 1.5, which is a feasible value. So if I choose lambda is equal to 1.5, d1 is 1, because sigma 1 square is less than or equal to lambda. D2 is 1.5 because sigma 2 square, which is 2, is greater than lambda. D3 is also 1.5. So now D is summation of di is 4. In that case, rate distortion function is half log 1 over 1 plus half log 2 over 1.5 plus half log 4 over 1.5, which you can write it as half log of 1.5 is 3 over 2 is 4 thirds. So you can just, since it's logarithm, you can, yeah, sum of logs is log of the products. So it's log of 1 into 2 over 1.5, or that's 4, 2 over 1.5. Okay, and then let me write this 20 over 15 into uh, 40 over 15, and half log of 800 by 225. You do the computation yourself, or maybe I'll do it. 800 over 225 is 3.55, and log of that is 1.83. Half of that is log of that is 0. No, 1.83. So half of that is 0. This also be 1.83. This is 0.915, which is option B. All right, that's it for today's problem solving session. I might take an extra class on Monday. I'm not sure. I that will just be a summary lecture where I'll go through all the lecture notes and write down most of the important results. That will just be useful for you guys to revise at the end, right before the exam. There won't be any problems in that session if I take that session. I'm not sure if it has been approved or not. Papers, I'm not sure where to find them. I haven't written the exam myself, so where can I find the paper? It's not released online, is it? Your exam, is it online or will it be online? Is it, then how will I find the question paper? I don't think they publish it, right? I don't have previous year question papers. Actually, I have not set the question paper. So I am an external TA kind of, so I only do the problem solving sessions. The people who set the question paper are TAs directly under Professor Adrish, so they will be from IIT Kharagpur. So you'll have to ask in the Q&A section in your course page. There will be a Q&A section where there's a email group, right? Click on the Q&A section. It'll take you to a email group. You'll have to ask there what type of questions will come, because those are the guys who actually set the paper. And professor is also included in that group, I think. I don't set the papers and I don't have access to previous year papers. All right. Good luck with the exam. I'll stop the recording. You guys can leave.